Alright guys, I am back for another video, and this one we're going to talk about a really important chemical concept. It's called buffers. Alright, it's called a buffer. And I'm sure you've heard the word, and you probably have heard the term in chemistry before, but it's very, very important. We're going to kind of walk through exactly what it is. Okay, buffers perform very, very important functions in the chemical world. What buffers do is they prevent a drastic change in pH in acid or base is added. Okay, so what a buffer does is it prevents a really large change in pH whenever I add an acid or a base to a solution. Now that's very, very important biologically because we don't want the pH of our bodies to change very much. We don't want the pH of our blood to change very much at any given time. So we have buffers in our blood that regulate the pH. And if a little acid is introduced or a little base is introduced, it doesn't really drastically affect the pH of our blood. Otherwise, the pH of our blood would be spiking and dipping, and of course that wouldn't work very well for our blood or for our cells. They have to remain in equilibrium, and it would just cause a lot of problems. So buffers prevent the pH from changing if I add an acid or a base. And they don't do this magically. It's not magic. It's science, believe it or not. That might shock you to realize. And what they do, they use something called an acid-base conjugate pair. Okay, they use an acid-base conjugate pair, and we're going to talk about what I mean specifically with that, and how that actually prevents the pH from changing. Okay, so we need to first talk about what a conjugate is, and what a conjugate base or acid-base pair are. So let me erase this definition here. Okay, so let's say we have our generic acid. Okay, so for example, this is our generic acid. Our generic acid is always written HA, all right, hydrogen and the anion. And then it's an equilibrium because we're going to be using weak acid bases. They're the only ones that make a buffer. Usually, they're generally the ones that make the buffer. Okay, and they're going to break apart and they're going to form a hydrogen and an acid. Now this could also be written as a hydronium if I react my HA to water. It doesn't really matter in this case because that's not really what we care about. What we care about is this HA. This HA is just called the acid. Don't know why I looked on my sheet for that. I should have known that. I did. This is the proton. Right, and this is a Bronsted-Lowry acid. It's a proton donor. It donates this proton. And then this right here is called the conjugate base. It's the leftover part of the acid. Now it's called the conjugate base because let's pretend this isn't in equilibrium. Okay, if I have it going this way, I have a proton donor, which is an acid, and it donates the proton and the other half. But let's say my equilibrium is going the other way. Well, in this case, I have my A minus, and it's accepting this proton to turn into HA. So this is accepting this proton. This proton goes over here, gets accepted by the A, and becomes HA. Well, hopefully this terminology is a little familiar because a proton acceptor is the Bronsted-Lowry definition of a base. This is a base. It's accepting the proton. And since this is an equilibrium, it's going both ways. So we have a weak acid donating a proton, and we have a very, very weak base accepting the proton. It's the acid and the conjugate base, the base formed from that acid. Okay? Now, let's say we have a weak base. Okay, so here's our second example. Our weak base is written B, and it's going to react with water. And it's going to form a BH plus an OH minus, and that pH is positive. Okay, so just like before, this B is our base. Ooh, that's a horrible B I just wrote. That's not making it any better. This is just, that's just a mess. Let me, there, no, that's horrible. Okay, well anyway, this is our base. That's obviously water. I'm not going to label that because you know what water is. This is our conjugate base. I'm sorry, our conjugate acid. My bad. This is our conjugate acid. And this is our OH, our hydroxide. Just like how the H plus is really the acid, the hydronium is really the acid, this is really the base. Okay? Now, just like before, if we notice, going from left to right, this B is accepting a hydrogen. So this is a Bronsted-Lowry base. It's accepting a hydrogen. It is not an Arrhenius base, right? This is not donating an OH. It's not donating an OH. That OH didn't come from here. It came from the water. It's accepting the hydrogen. It's a proton acceptor. It's a Bronsted-Lowry base. Now, if our equilibrium is going the other way, we notice that this H is being donated. It's being donated. Goes over there to form water. It's being donated, and it's a proton donor. And proton donors are acids. So we are accepting the proton going from left to right, and we are donating going it from right to left. So we end up having this pair, this acid-base pair. And they're called conjugate pairs. They're conjugate acid-base pairs because I have an acid forming a base and a base forming an acid. Okay, so that's what we mean by when we say conjugate acid and conjugate base. Okay, now it's very, 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 very important to realize something very simple. For all intents and purposes, this is always true. For all intents and purposes, this is always true. This is how a weak acid always reacts. This is how a weak base always reacts. Okay, so if you know how a weak acid and a weak base interact and react with water, it's always the case. Please, please, please don't make this harder than it has to be. Okay, this is how a weak base forms an OH. This is how a weak acid forms an H. There's a lot more things in AP chemistry to make difficult. Please just leave this alone. Okay. Now let's talk about what actual buffers are. So let's talk about what actually buffers are. Okay, so buffers. There's a couple of different ways I can form a buffer. Okay? One way that I can form a buffer is just taking a weak acid and putting it with its salt. Alright, taking a weak acid and putting it with its salt. Another one, might not shock you, is to take a weak base and put it with its salt. Okay, just take a weak base and put it with its salt. So those are the two main ways. Now there's other ways that have to do with reacting a strong acid with a weak base or a strong base with a weak acid. But these are the two big ways. You take an acid, a weak one, and put it with its salt. Now, the salt is going to be the conjugate base. It's the conjugate base, or I guess I should say, or it could be the conjugate acid, depending on whether or not we're using a weak acid or a weak base. Okay? So let's say, for example, let's say I wanted to make a buffer with hydrofluoric acid. Okay, so hydrofluoric acid is HF. That's going to form an equilibrium with H plus and F minus. Okay, this is a weak acid, dissociates. So here's my acid, here's my conjugate base, this is my proton. Okay, the salt of HF, would be something like, I don't know, NaF, sodium fluoride. Okay, sodium fluoride. When sodium fluoride dissolves in water or dissociates in water, it's going to form an NH plus, which is just going to be a spectator ion, and it's going to form an F minus. Well, that F minus is right there. So what we're doing is we're taking a weak acid and we're essentially adding the conjugate base of that acid in there. So we add the HF, and some of it will dissociate, but it's weak, so not a lot of it will. So I'm going to have very little H and F minus. So I take HF, I pour it in a beaker, and I take some of its salt, sodium fluoride, and I put it in the beaker as well. That way I have higher concentrations of both my acid and conjugate base. If I didn't do that, I would just have a whole lot of HF and very little H and F. I'd have a lot of this, very little of this. So by putting in the salt, I have high concentrations of this, and I also have high concentrations of this. All right? Now what that's going to do is if I add acid, if I add hydrogen, well, the F can react with the H and form HF. Okay. And if I add a base, the HF can react with the base and form F minus. So it's going to act both ways. All right, it's going to allow, let me get rid of this, it's going to allow both a base to react with something and an acid. I have both an acid and a base. So no matter what I add, if I add a base, it's going to react with the HF. If I add an acid, it's going to react with the F minus. So no matter what I add, it's going to react together. And this is true for anything else. Let's say I wanted to do a weak base. I would add NH3, and then I would add the salt of NH3, which is, let's say, NH4Cl, ammonium chloride. And so what that's going to do is the Cl is going to be a spectator ion and just kind of float off. Here's my base. Here's my conjugate acid. So if I add an acid, it'll react with the ammonia. If I add a base, it'll react with the ammonium. Or vice versa. I can't remember which way. Okay, so that is buffers in a nutshell. There's a lot more about buffers that we'll get to in class, but this is a good kind of introductory lesson. All right, good luck.